Welcome back. A model rarely just says yes or no, it gives a probability, a confidence. When it says it's 90% sure, should you believe that number? Not always. Today we learn to check. Here's a single prediction. The model doesn't only label this transaction fraud. It also reports a confidence, 92%. That extra number is the whole subject of this lesson. And that number does real work. Below 30%, we auto-approve. Between 30 and 80, a human reviews it. Above 80, we block the card. Every one of those actions trusts the confidence. So the confidence itself has to be honest. Here is the question that defines calibration. Of all the times the model says it is 90% sure, is it actually right about 90% of the time? If yes, we call the model calibrated. To check, we gather many predictions and sort them into buckets by confidence, the least confident on the left, the most confident on the right. The height of each bar is how many predictions fell into that bucket. Take the most confident bucket. Here the model claimed about 97% sure, on 150 predictions. Now count how many were really fraud. Only 132 of them. That's 88%. It claimed 97, but was right just 88. It overstated its confidence. Let's plot this for every bucket. Across the bottom, the confidence the model claimed. Up the side, how often it was actually right. The green diagonal is perfect calibration. Claimed equals actual. A model on that line never lies about its confidence. Now each bucket becomes a point. Claimed on one axis, actually right on the other. Bigger points hold more predictions. And the points do not sit on the diagonal. The whole curve is too flat. Reading it is simple. A point below the line means the model said high but was right less often, overconfident. A point above means it said low but was right more often, underconfident. This model exaggerates at both ends. We can boil the whole picture down to one number. Measure the gap from each point to the diagonal, weight it by how many predictions are in that bucket, and average. That's the expected calibration error. For this model it's 12.5%, a big gap. Why care? Because every decision we built earlier reads that confidence. A 90 that's really a 70 quietly corrupts the approve, review, and block rule. The lie propagates into every action. The fix is gentle. We don't retrain the model. We just rescale its confidences. This is temperature scaling. Divide the model's logits by a single learned number, here about 2.1. It softens overconfident probabilities toward honest ones. Apply it, and watch the points move. They snap onto the diagonal. The confidences now match how often the model is actually right. The calibration error drops from 12.5% to 3.2%. And notice, the accuracy is unchanged, still 73%. Calibration fixes the honesty of the confidence, not the decisions themselves. So, to recap, a probability is a promise, and it has to be honest. The reliability diagram checks it, claimed versus actually right. The calibration error captures the gap in one number. And calibration changes the confidence, not the accuracy. Next, we ask a deeper question. Can we explain why the model decided what it did?